Are you sitting comfortably? Good. Then we'll begin.
So Dr. Fleischmann showed you some very simple example. This is for one volume in like a cubic volume uniform, and what happens when you change various parameters. And you will have the program in the lecture folder. By the way, I want just a little bit of feedback from you. Alice?
Yes.
Okay, I just want to make sure that everybody is getting my message now. So after I switched, so you hear me, yes? Okay. So I guess I assume that everybody else is watching me. Okay, let's continue. We have 20 minutes left, and I will try to go through the rest of my presentation, but I will share my screen now. Okay. And I will start to launch GX simulator, and I'll say GX, and I will just put a parameter. Let's put 2. For this means I will launch it with 2 parallel threads. So this is the way you would launch GX simulator. Okay, and just a moment, I want to make sure that okay, I see you guys here. Okay, so it should be fine. And I will upload the model. So here is the main button from it. You can upload a saved model. And I will go in your lecture folder. Remember that I shared with you a folder which had lecture 1, 2, 3, 4. Last lecture was lecture 5, which is not no material, but today lecture is lecture 6, and I said that it's 2017 just to make it different from the previous one that were recorded in 2016. And in this folder, if you go on your WebEx account, you'll be able to access 2 models, and the one that I will upload is one called peak time, which is modeling solar atmosphere and the magnetic field loop during the peak time of a flare. This flare happened in 2002, April 12, and was observed by our observatory in Owens Valley. So when you open a model, you have to be a little bit patient because there are a lot of information that was saved with the model. And you might get some messages back, which I will ask you to ignore for now. I'll show you in a minute. But it will take a while to, for example, you don't need to update anything at this point. And what we have here is a model, and what you see here is some kind of density in the volume. But let me hide. I have here a button that says hide button because I want to show you what is inside the what we have. We have a magnetic surface, yes. So here we have the magnetic field at the bottom of the cube, and we have field lines in the model. In fact, if you want to inspect the model itself, you can click on this button and say zoom to the model, and you can manipulate and understand what is this model about. And if I show density, you will see something here, but you don't see very much the loop because you have much more density surrounding the loop. But I will show you something that Dr. Friedman was talking about. This is actually thermal density. This is the temperature inside the volume, and here you see that the loop is hot. Yes, compared with the surrounding. There is temperature outside, but the loop is much hotter. And this is another parameter, which is density of the emitting electron, which are also here in the distributed along the loop. And another parameter that we're talking about was the magnetic field, which, yeah, you won't see too much because it's everywhere. But let's go to the model. And now there is one thing that you have to remember, and even if you don't remember when you watch the recording, you'll remember, is that this particular model was obtained under the assumption that the observer was looking directly from above of the model. So to simulate this situation, you have to click top view. When you click top view, the cube itself changes a little bit the position, but let's go to this. So what you have to do after you change the orientation of the model, you have to compute inscribing field of view. And this is not all. You have also to compute the rendering grid, which might take some time. And now you can zoom to the field of view, and this is your model. So now you see what is the top view. You look at the model from above, directly from above. So this is magnetic field, you see it. But there is a tab here which is called line of sight profiles. And now this is the slicer that goes through the model, and you see this slice goes perpendicular to the cube. Actually, the cube is here. Okay, so the slice is going like this, and is slicing this model like this, and you see through the volume in Z direction, and this is X direction. So let's go back. And again, so you can move here like a cursor, which gives you this point, and this is the line that's going through the volume in vertical direction through the volume, and tells you what is the distribution of the magnetic field along this line of sight, which is perpendicular on the screen. Your eye is looking in this direction. Now, let's go back to temperature. And you see temperature, now you see slice from the temperature. You see the temperature is changing in the volume. Now I can slice my model and I see different temperatures. And let me show the temperature. So this is what I'm slicing now. And you see just a cross section of this loop. And here you can look at the thermal density. And now you can see, even if you don't see through it because it's very thick here, but the slides will show you what is going on inside the volume. So this is thermal density. You say this is the background, the blue one, and this is just the loop that is crossed by the slicer. And non-thermal density, which this emitting electrons are just assumed to be in the loop, nothing outside the loop. That's why it's transparent outside, and you see the distribution of the emitting electron in the loop. So now, when we do this, you are ready to. So how did we obtain this, by the way? It's a tedious process, but at this point we don't try to reproduce. But you see, you have to create a flux tube, and the tool allows you to create a flux tube. I will show you how you can create one, but you don't have to do it at this point. So the idea is that if you right click here and say create a fill line, you can create field lines that start from any point. Yes, but the one that we created here is one that is going from here to here, from positive to negative, and we were looking for various field lines that allowed us to model what we see with our instrument. So now, if you look this clean, well, it will clean everything but the one that is locked here, which is the flux tube I'm interested in. Let's go again to XY direction, and I want to show you that actually when I say, sorry for these annoying messages, but it's something that, okay, no, I don't want to compute it. So you say these are maps observed by NGIT at different frequencies, and we try to model a loop that will emit in this the same as the observation. So some emission along this path, and is how we selected this loop. And when you create a flux tube, you can control how big is the cross section, and you can control different parameters, and one of them is thermal density, which is 10 to the 11 per centimeter cube, temperature of the loop, which is 2.4 10 to the 7, which is like 24 million Kelvin, and non-thermal density, which is which is 80 million per centimeter cube, and so on. Okay, so these are numbers, which I will you will have some point to play with. Yes. I will, by the way, I will update the volume to not give you the model, not to give you these annoying messages when you play with it, but I will do it later this afternoon. Sorry for this again. So let's see what is the next step. Once you put everything that we think that the model needs to have inside, all the parameters, we have to select which rendering method to use. And when you say select radio flaring, if you are on Unix, you go to Unix. If you are on Windows, you go to Windows. And if you have a 64-bit system, you go to a 64-bit system. And here you choose something that is called GX Transfer Lite. The first one is a good choice. Just open this. And this actually gives you a list of parameters, the same as you saw in Dr. Fleischmann program. But you don't have to change these numbers here, because the numbers are actually changed through this interface. So that table is just an interface with a dynamic library that will compute emission. And at this point, we go to image view, and we start producing emission. And these are maps at different frequencies. Okay. And you can look the progress in this tab scanner, which is 63 out of 64. So basically now we have what we produce. We produce maps at 100 frequencies, which start from 1 to 100, close to 100 gigahertz. And our observation goes from 1 to 18 with Owens Valley Solar Observatory. But let me show you, there is another thing here, say image profile. And here is what Dr. Flamer told you about it, is, okay, what is the spectrum in this point? So it looks something like this. If you go to another point, it's a different spectrum. This tells you something about, in this location, along this line of sight, we have some density, some magnetic field, and some temperature. So all of them plays a role, and they build a local spectrum that looks different in different points. So this is our, that's going from what Dr. Flamer showed you for one single volume, element of volume, to a more complicated model in which we want to put together numbers and try to model the 3D volume. So it's a very challenging task, but this tool allows you to do that, because now, once we have this is pixel by pixel, but we can also say, okay, what we observe if we integrate at each frequency, we add up the emission from the entire field of view. And when you do that, I know that you have to finish in 5 minutes, so I'll finish, don't worry, but I just want to change here image. Okay, so this is the spectrum. Now if I change frequency, this spectrum won't change, because for each frequency is just one number. And we add up everything, all this added together give you 95, this point here. When we go to 1 gigahertz, all this added together give you this much. And the peak is somewhere here at about 10 gigahertz. So this is where the emission is stronger, something like that. And now, the magic thing is to open a reference spectrum and go again to the lecture. And this is integrated flux from our instrument. And this is time. So how in time the emission change. And what we try to model here is something 1755, no, 45, 09, okay, which is the peak of the flare. So you see what we realize here, actually the number that we put in, they match the observation pretty well at a given time, which is the peak, the maximum peak of the flare. And this is true only for the parameter that we put here. And just to give you an example, you can play at home trying to change things. So go here and just try to change something. For example, let's suppose that the non-thermal, instead of being this much, is 10 times less. Go to scanner, build the maps, and look at the image, and you see that no longer matches the observation. See? So the numbers that are there are not random. So this is what you'll have to do to play with this number and try to match observation.